Any questions, guys? Do you have any questions from the previous lecture or any lecture, any other lecture as well? Do you have any questions there? No questions? Can you hear me? Is my sound clear?
Clear.
Yes.
Clear.
Let's start. Last time, what we did was about the important features. Close your mic. Whoever it is, please close your mic. Okay. So last time we talked about the important features or characteristics of a crystal structure, which were the coordination number, the atomic packing factor, the close pack directions. We said that the coordination number is the number of touching or nearest atom actually to any of the atoms there. Yes?
Are you sharing the screen?
Yes, I am.
I can't see anything.
You guys all cannot see the screen?
اوكي دكتور.
نشوف الشاشة.
عندك مشكلة؟
I can.
إيه. انت بس ما تقدر تشوف صح؟ سوي ريلود، سوي ريفرش. Do something. Okay? Is it coming now? What's your name? اختفى.
اوكي دكتور خلاص الحين اشوفه.
تمام. So we talked about the coordination number, which we said is the number of nearest or neighboring atoms there. We talked about the atomic packing factor, which we referred to as, in short form, we said it is the APF, and we said that this is basically indicates how filled a unit cell is, or the lattice of material if you want, or in general. And we do a calculation for that, of course. And we talked about close pack directions as well. We said the close pack directions are directions where the directions in the lattice or in the unit cell where the atoms are closely packed together, which they are in those directions, they are touching basically. So these are the things that we said, and we said also last time that in order to calculate, so these three things we need to determine because they are important characteristics of the crystal structure. Important characteristics of the crystal structure. So we are going to determine all these three for every crystal structure we are going to look at. We'll do that today. In addition to that, we said also we need to determine also some other characteristic, which is the number of atoms per unit cell in order for many physical properties, but important property, which is the atomic packing factor, the APF. We need to calculate the number of atoms per unit cell in order to calculate that. We will see those in the equations. Now, that is important to understand. So we want to go now next, which will be the number of atoms per unit cell. How do we look at that? So let us start with the simple cubic. And the simple cubic looks like this. This is a cubic, simple cubic, and which means also that you have an atom in each corner, which we did last time. We said we are going to one, and we are going to look at the atoms, each atom, which we assumed the hard sphere model, in which we assume that the atom is a hard sphere, and we place that in each corner of the cube. That's the cube. So we placed a hard sphere model in each corner there. That corner, that is the lat. This is actually not the lattice. The atoms are showing there. Now, if we look at only the position of the atoms, the points I'm putting here now, the positions of the atoms there, just to revise also the definition of the lattice, the position of the atoms, which I'm showing by points there, is called the lattice. Of course, this is the material altogether, and that is a unit cell. And we said last time that the unit cell is the smallest entity that exhibits the chemical and physical properties of the material. It's the building block. Remember, I gave an example of a wall. So we can also refer to it as a building block, which I can use to study the whole material by studying only the unit cell. This minimizes actually the cost of a study when I go to only studying a unit cell, the simplest possible unit entity, which can give me the characteristics of the whole material. So now imagine that you have a unit cell we want to look at. In this unit cell, you can see these are corner atoms which are there, and here and at the back as well, and each atom has. So if we cut a unit cell like that, of course not all the atom parts will be inside this unit cell, only part of the atom will be inside that unit cell, as you could see there. So how much of an atom is inside this unit cell? You can see my pointer clearly, guys?
Yes, doctor.
Yeah. So how much of that atom can you imagine, without me telling you, how much of that atom is inside this unit cell? This is a volume, a unit volume, which has a length of equal length. This equals to this equals to that, because we have a cube. So how much of that atom do you think is inside this unit cell, guys? Yalla, give it a minute. Not
Quarter.
a minute. Quarter يعني ربع قاعد تقول صح؟ You're saying 1/4, right? Look at it a little bit more, please. A little more, because this, you are seeing a circle there, but this is a volume. That atom is a hard sphere, right? Sphere. It's a volume. It's being shared by how many unit cells actually? It's being shared by this unit cell, which is here, and it's being shared also by other unit cell there also. So if I draw this to the back, then, and it's being shared by this unit cell also, صح? So I can draw that line here and like that. So this unit cell is shared by actually half of the unit cell down there, as you can see, which I am pointing here. Half of the unit cell, the lower part of the unit cell, is not being shared by only two units, half of the atom which you see there, which is the hard sphere model, is being shared by this unit cell and that unit cell, but also behind these unit cells, in the front of these unit cells, yani in the front of this, we don't show the atom, we're not showing the atoms there. There are other unit cells as well. And here, you can see there is a unit cell, and here also we have another unit cell here. All right, and this goes and continues like this. So the lower part here is shared between this unit cell at the back, and this unit cell, and this unit cell, and the one below this unit cell. And the upper part is being shared by this unit cell, and this unit cell, and two, which will be here. There, and another one here.
يعني دكتور راح على 8.
8 صح؟ You figured out صح؟ بعد التوضيح شوية, you could figure out that this unit, the half of the unit cell down, is shared by 4 unit cells, and the other half, the upper half, is being shared by another 4 unit cells on the top. So this means that that atom is being shared by 8 unit cells. ولا لا? Clear شباب؟
كلير دكتور.
The other guys, if this is not clear, please raise it now. Any of the students, please.
دكتور ليش 8؟
ليش 8؟ شوف ما احنا رسمنا له. This is one unit cell. This is another unit cell. صح؟ Let's look at to start with the other way around الحين. This atom which we have, I'm focusing at one atom only. This is the atom I'm focusing at. Has two parts, the lower part and the upper part. Look at the upper part. It falls in how many? It's in the middle. So it falls in how many unit cells? Because it's a sphere, it's not a circle. Imagine that. It falls in this unit cell and this one, the neighboring one, and the one in front of it, and the one in front of this one. So the upper half is being shared. نص الأتم, نص hard sphere, is being shared by how much? Because so if you look at that from the top, of course, it will be like this because it's a sphere. So it's being shared by 4 actually. Each of these falls in one unit cell. So 1, 2, 3, and 4. 1, 2, 3, and 4. Each one falls the upper half. We're talking about the upper half. The unit cell ends there. So the upper half is being shared by 4 unit cells. 1, 2, 3, 4. And the lower half is being shared by the lower unit cells. 1, 2, 3, and the one at the back there, 4. So this means that one atom is being shared by 8 unit cells. Did I make it clearer, or there is any issue still?
كلير دكتور.
Clear. So if we are convinced with this, then we know that each atom is being shared by 8 unit cells. This means that how much of an atom, let's go to this figure. How much of an atom is this or this, the corner atoms? How much of an atom is there in that unit cell? كم من الاتم هذه موجود في اليونت سيل دي؟ How much of it? It's divided into 8 unit cells, so it is 1/8 of an atom. ولا لا؟ Each corner atom is 1/8 of an atom. صح؟
صح دكتور.
عدل شباب؟
عدل.
مو بس واحد، كلكم.
عدل دكتور.
عدل. So if you are okay with that, this part of the atom which is being shared by the others as well is 1/8 of an atom. How many of those do we have in one unit cell? In the simple cubic which we are showing here, we have 1, 2, 3, 4, 5, 6, 7, and 1 at that corner which is not shown. So we have 8 of them there, صح? We have 8 of the 1/8 of an atom in that unit cell. So if we have 1/8 of an atom times 8 of the 1/8 of the atom, which means that we have actually 1 atom in each unit cell, isn't it? عدل شباب؟
يعني دكتور الجزء الواحد يتشارك 8 وهو كله في اليونت سيل واحدة في 8.
في كل يونت سيل في 8 كورنر اتومز، صح؟ طبيعي. في كل يونت سيل في 8 هكا. How many are they? 1, 2, 3, 4, 5, 6, 7, and 8. These are 8 corner atoms, صح؟ These are 8 corner atoms. Now, each corner atom represents how much of an atom? It represents 1/8. ثمن الاتم موجود فيه. إذا ثمن زائد ثمن زائد ثمن زائد ثمن زائد ثمن زائد ثمن 1/8 8 times, which gives you 1 atom. So total number of atoms due to the corner atoms in one unit cell is 1 atom. واضح شباب؟
دكتور، فهم مقسمين لأجزاء وكلهم يا بعض يساوون أتم واحدة.
كلهم مع بعض they make a volume of one atom.
اوكي.
عادل ولا لا؟
اوكي الحين فهمت دكتور.
شباب وياي؟
وياك.
في احد مو واضح عنده؟ Okay. If you need, this is what I'm saying, you should be able to convince yourself that in simple cubic crystal structure or a simple cubic crystal structure, which is this one, because we have only corner atoms there. The other type of crystal structures will be different. We will look at those. They contain what? One atom per unit cell. So the corner, the simple cubic crystal structure, they contain one atom per unit cell. This is an important number which we will use to in many physical properties, but one of the physical properties that we will be using is the atomic packing factor, which is the APF. To determine that, we need this number. So you need to remember that a part of each atom is shared by another unit cell or other unit cells. This is how it goes. Yani this atom is being shared by another 8 unit cells there in the lattice, and that's why each one consists of 1/8 of an atom. This is what we were saying. So the yes.
Why is it called simple cubic crystal structure? Why the term simple? Do we have other cubic crystal structures?
Yes, exactly. We are going to come to this. Last time we are already maybe mentioned that. We said the simplest is what we have already seen now. We have others also. We have the body center cubic, which we abbreviate, or the short form for it is the body center cubic. And we have the face center cubic, the FCC crystal structure. We have the hexagonal closed pack, the HCP crystal structure. Of course, we have more than 15 or 16 types of crystal structures. We are going to look at the most common. Last time I said these 3 are the most common crystal structures. We are going to look at these only, and the simple cubic as well we are going to look at, but the simple cubic is not a common one. It's actually rare, but we normally study it because it's the simplest one, and it simplifies looking at the other ones as well. We will at a stage look at the different types of crystal structure as well, but we are not going to study them because they are more of a concern in chemistry rather than materials. So we are going to look at the most common ones here in material science that we need for the materials. So the number of atoms per unit cell, as I said already, we can determine several mechanical properties, one of which is the atomic packing factor. In general, for the crystal, for all the crystal types, not only the simple cubic, the number of atoms per unit cell can be given by n, like this is a generalization formula for the number of atoms per unit cell, which we can calculate. We can say it's equal to Ni plus Nf over 2 plus Nc over 8. Now, of course, this is a general formula which stands for the simple cubic, the body center cubic, the hexagonal closed pack, the face center cubic, for all of those. But with certain limitation, we will look at that later. The Ni stands for the interior atoms. Is there any interior atoms inside there? No. So for this case that we are having, this will be 0. We don't have any interior. We only have corner atoms there, so that will be 0. Again, in this case, do we have any phase atoms here? Phase atom means that you have some atom in the phase here, or the phase here. The phase, يعني في الواي. We don't have any phase atoms there, so in this case, this is also 0. In the simple cubic, this is also 0. In this case, the simple cubic, we have corner atoms. Nc stands for the corner atoms there. We have corner atoms. Yes, of course, we have corner atoms. How much is that? We have 8 corner atoms, which we already mentioned this. We have 8 corner atoms there. You can see those. And 8 divided by 8, it will give you 1. Which is the same result that we had here. It is number of atoms per unit cell is 1 atoms per unit cell only. So this is a generalized formula. If you want to know it, it simplifies the addition of or determining the number of atoms per unit cell. To revise, there are some points that we need to revise together to know what we are doing and what we will be doing. One important thing, let me go to this at the end better. Let me look at these are simpler. The coordination number is the number of the nearest neighbor atoms, which we are going to determine for every crystal structure we are going to deal with. Coordination number is an important characteristic of the crystal structures of the materials. We can, using the coordination number, basically we identify what type of crystal structure we have. So شنو فائدة إن نعرف coordination number? Normally, how do the meteorologists know the type of crystal structure we deal with? Well, using microscopes with high magnification. Normally the coordination number is studied. How many atoms are touching one of the atoms, for example. From the coordination number, they know what type of crystal structure it is. So it is important to know the coordination number there. One thing we mention about coordination number is that large atoms tend to have large coordination number. CN stands for coordination number. And small atoms usually have a small coordination number. Yani if you have a large atom, where is the if you have a large atom compared to a small atom, a large atom can have more atoms touching it. Yani why? Because it has a much bigger surface there, so more atoms will be touching it there. The possibility of atoms touching it will be more. On the other hand, a small atom can be touched by a limited number of atoms. So the number of atoms which are touching a certain atom, when the atom is small, the coordination number is small. When the atom is large, the coordination number obviously will be bigger. So this is what, to end up, we are saying it is easier to surround a big atom with lots of atoms than a smaller atom. So basically, this is just a revision of what we have already done. Another note which is important also about the close path directions. I'm saying here the energy required for the slip to occur in the close path directions are much smaller than that in the non-close directions. And you know why this actually here I am implying the importance of the close path directions. What are close path directions? Are directions where the atoms touch one another. Yani, what's the meaning of that? Any atom in the crystal structure touching another atom like that, if in that direction the atoms are touching one another, this direction which we are referring to is called a close path direction. Okay, a close path direction. This is a close path. Close path, yani closely packed. Yani there is no, there is no space in between them. So why is it important to know the close path directions? Well, basically, because the close path direction, and this is what I'm saying here, the energy required for the slip to occur in the close path directions are much smaller than that in the non-close path directions. You remember when we talked about the slip, or let's say previous to that, we talked about elastic and plastic deformation. We said elastic deformation or recoverable deformation, it involves only the stretching of the bonds between the atoms, and that's why for the material to go to its lowest energy level, it recovers its initial dimensions. It goes back, it springs back. On the other hand, plastic deformation happens due to dilatation. Which is dilatation basically? It happens due to the movement of large number of dislocations. These dislocations, when they move, they cause the slip in the material. When the material has slips in them, they dilate, they move, and they cause this plastic deformation. So the movement of the dislocation causes the slip, which happens in the material, and the slip causes the plastic. They add together. We talk about hundreds of thousands of dislocations all moving in the material when the material is stretched. This movement of the dislocations causes the slip, and all those slips add together. They will make the total plastic deformation in the material. So this is something which we had before. How does plastic deformation occur? Now, the movement of the dislocation does not happen in any direction. Of course, it can happen in many directions, but it doesn't happen in any direction. Why? Because there are favorable directions where the slip or the movement of the dislocation happens. Why? Because there are directions which are called close pack directions. Those directions require less energy, less stress, less force in order for the dislocation to move. And therefore, the dislocation will not choose to move in directions which it requires high energy, high stress, or high force. It will choose to move in directions where it requires less force, less stress, less energy. صح ولا لا؟ So this is where
يعني دكتور
أيوة.
هو على طول السليب بيصير في الكلوز باك دايركشن.
Yes.
نقدر نقول على طول.
Norm. This is the norm. الحين أنا let me explain it in this way. Let's say if you have a tank of water, and you have a pipe coming out. Let's say this pipe is going like this, and another pipe, and I'm going to arsom another pipe. I should have drawn cylindrical, but let's say this is one option. The other option is that the pipe is going up like that. And the third option is that a pipe is going down like this, and the tank is filled of water, right? Where will the water flow? If these pipes are open, where will the water go? Will the water go up?
لا.
Will the water go here? Or
لا.
the water will go there?
آخر واحد.
The water will most probably choose to go in the lowest energy required, actually, and this is the one. So the material does the same thing. If you have as a person, if you have different routes to follow, you have this route to follow, and you have another route to follow, which is like this, and a third route to follow, which is like that. And you are given the options. Which route will you follow? You will follow that which is easiest, isn't it? You will not go zigzagging there, nor you will go there where you have more obstacles. You will not choose that as well. You will choose the easiest one where you don't have resistance, for example, like this. So you will choose the easiest one. Material does the same thing. If within the material can flow, slip can flow, or slip can move in that direction much easier than the other direction, this slip is going to happen in this direction, in the close pack direction, rather than going, and because this is what naturally happens when you are stretching a material, as we did in the tensile testing. We start with a load, and we stretch, we go at a constant rate, the displacement of the cross head will be constant at a constant rate. but the force will be changing. As we stretch more, we need to apply more force there, right? Now, as we are applying the load starts with a small amount. So obviously, in the directions of the close packed direction, which it requires less energy, the slip is going to, the dislocations are going to move. Not in the directions where it requires higher energy. In the other direction, we have the atoms are displaced from each other, and this direction requires more energy. Obviously, the dislocations are going to move in the less requiring energy directions rather than in the bigger energy requiring directions, isn't it?
Yes.
واضح شباب؟ guys
واضح.
واضح؟ Any
واضح.
question? If there is any issue, please raise it now. We are in it. So, in the close packed directions, the energy required for the dislocation to move is less than in the other directions which are not close packed directions. You see a gap between the atoms there. A gap between the atoms. So here the force required, the stress required is more. Obviously, the dislocation is going to move in the other direction, which requires less, and this is what less energy. So this is why we say the dislocations don't move in any direction; they move in favorable directions, which are referred to as the close packed directions. Now, another issue: if this is clear, we can move one step further. Guys, I need just you to tell me if this is clear ولا لا علشان اروح حق النقطة اللي عقب. Clear شباب? Any doubt there? So, if there is no doubt there, I'm pausing a little bit just for somebody who is hesitating to ask to be encouraged. يعني. If there is no doubt there, why do we say that the directions where are not closely packed requires more energy than the directions where it is closely packed? Well, I can explain that from the mechanics point of view, but also you can look at it in the way that we normally tell the students also, that imagine moving without wheels. يعني هني there are wheels all. I will not continue drawing circles, but there are wheels all through. So the wheels will be carried on the ground. The machine or the car is going to move. But here you have a gap, as if you don't have a wheel there. So the movement will be more difficult. Imagine a car missing one wheel. How will it move? There will be more difficulty to move there, صح? So with a gap there, it is more difficult, as if we are looking at a car with one wheel missing. So it will be more difficult to move in that direction rather to move in this direction. Another way to look at this from the mechanics point of view, imagine that you have, let's say, a chair here, or a car if you want, and I prefer to say box, yalla, since I'm drawing two boxes there, two boxes here, and in the other case, just to compare both, the two boxes are, closely packed. They are touching one another, like in the direction of the close pack. Imagine if we want to push this with a force, because this is what we do when we stretch the material. We push it as if you have a stress there, pushing the dislocations to move. So imagine that you want to move these in this direction. The force which you require to do that, or the stress which you require to do that, will have to overcome the shear stresses which are there and the shear stresses which are there. So you need to apply more force than these two added together in order to make the things go in this direction. صح ولا لا? This is what happens. In the other case, let's say we have similarly, what force do we have to apply? There. If dash, what force do we have to apply? Well, again, the same thing. You have to apply this, and when they touch each other, there is also another one here. So you need to push both of them in the same way. So in order to push in this direction, in this direction. So you need to apply a force which is equal to this and that. But not only that, when this gap is closed, then this is going to impact here. And when we are looking at this, of course, this is from the mechanics, from the micromechanics actually. If we are talking about an atom here and an atom here, these are two atoms only, but in reality we are talking about millions of atoms like that, which are not closely packed in the same way here. So we are talking about millions of atoms there. If you move this, if you want to move this, once you move this, it's going to hit here. It's going to impact. And when this atom impacts with the other one, or this box impacts with the other one, there is what we refer to as every action has a reaction. That impact would have a reaction which is in the opposite direction. So in addition to that, this force needs to overcome this force, and this force, it needs to overcome that force as well. So in generally, this force then needs to overcome three different forces there, while this force in the close back direction needs to overcome these and these only. So this force obviously will require this direction will require more force here than this force there. So this is just a simple explanation from the micromechanics which happens at the atom levels there, which when we deal with it as hard spheres. So of course there we are looking at two entities only, or two boxes, or two atoms, or two cars. But when it comes to be millions of atoms there happening in the same way, the additive forces will be large, as we see. So this is to explain why in the close back directions you require less energy or force or stress compared to the non-close back directions where the atoms are not touching. You have more energy required, more force or more stress required for the dislocations to move in those directions, and therefore cause the slip which can occur in the material, and therefore will cause the plastic deformation in the material. The more difficult it is for the dislocations to move, the more difficult it is for the slip to happen. The more difficult it is for plastic deformation to happen, the stronger the material will be, and the harder the material will be as well. The easier it is, which is the cross-back direction, is the easier it is for the dislocation to move, the easier it is for the slip to happen, the easier it is for the plastic deformation to happen, the weaker the material and the less the hard the material will be. So this is how we are putting it. Any questions?
دكتور نقدر نقول ان البوليمرز كلوز باك لان هو ضعف.
We are looking at metals here الحين, and specifically we of course all the metals are like that, crystalline. So we are looking at crystalline materials. In the polymers, you have a completely different story there. Here we are talking about crystalline materials, where يعني لما نتكلم عن crystal structure, we are talking about crystalline materials. This is what we said at the beginning of the lecture in this chapter, that we are going to look at solids, and specifically we said we will be looking at crystalline solids, and then we compared crystalline and amorphous crystal structures to just compare the two. In the polymers, you have something different, which is called the viscous flow. We are not going to cover it here. The chapter is all concerned with crystalline material. هناك يصير شيء ثاني اللي يسمونه crystal flow. You remember, just since you asked, my goodness, time has passed a lot, but anyway, since you asked, you remember there we had long chains. I don't have space here. Here is black. Can I draw here? No. Anyways, yeah, I can draw here, no problem. Then we can erase. So in the polymers we had long chains, remember, and another long chain, and another long chain, and another long chain. Hopefully I will go in between these. Oh good. And these chains had, for example, if this is carbon and this is hydrogen, and it was continuing like this, you get me, right? So this is carbon, this is hydrogen, صح؟
اي دكتور نفس الرسمة اللي عندنا اياها في
أيوة نفس
السلايد
الرسم اللي عطيتكم. So what happens when you are
مالت
stretching
البوليمرز.
there? Yeah, what happens when you are stretching there? These are covalent bonds between the within the chain. You have covalent bonds there, and between a chain and another one also you have a bond there. But we said these bonds are weak hydrogen bond or van der Waals bonds, which are weak and insignificant. Yani small amount of energy will be able to break them. Now, if you are heating up the material, we said these bonds break, and that's why the material, melts easily. If that's the case where we don't have cross links there, like in the thermoplastics, so the material melts. In the same way, if you are stretching the material, you are pulling it. You're pulling it like this. What happens is also very similar to that is that when you're stretching it in between if you look at from the microscopic point of view, then you will see the chains there. These bonds break and these chains viscously flow above each other and cause the plastic deformation of the material. So in the polymers, it's a completely different mechanism and different issue compared to the crystalline materials that we are talking about. This is just a fast answer to your question. You're satisfied?
تمام دكتور.
Okay.
دكتور عندي سؤال.
اتفضل.
دكتور في الميتالز في نان باك وكلوز باك مع بعض ولا كل مادة لها شيء واحد يعني؟
من أول ما فهمتك. من أول؟
أقول يعني الكلوز باك يعني في كل مادة فيها كلوز باك ونن كلوز باك ولا كل مادة
there is, of course in every crystal كل مادة أنت قصدك كل مادة إحنا نبي نركز على crystal structure. في مواد there are materials which have common crystal structures. So we will see now. الحين we are already finished with time. Next time, what we are going to look at, we will be looking at the simple cubic crystal structure, the body center cubic crystal structure, the face center cubic crystal structure, and hexagonal close-packed crystal structure. In each of one of these, I will show you what is the close-packed directions in those. What is the, not only that, but we will look at also the coordination number, the number of atoms per unit cell, the atomic packing factor. We will be calculating each one of these for those crystal structures which are common crystal structure, in addition to the simple cubic crystal structure as well. We are going to do that. You will see that in the BCC, close pack directions are different than the simple cubic. It's different than the hexagonal close pack. It's different from the body center cubic crystal structure. And this also applies to the rest of the other types of crystal structures as well. يعني كل crystal structure close pack directions ماله غير. شلون يطلع لي انا؟ شلون يطلع لي؟ presenting. Okay, did I answer your question?
Yes.
شباب? Okay. Any other question? Because I think we finished time, صح? Time is finished, صح؟
Yes.
دكتور.
ملتبس علي شيء. Okay, so I will stop here. Do you have any other questions, please?
دكتور نقدر نحول الكلوز باك لنون كلوز باك.
انت على اي ليفل قاعد تتكلم هني؟ just يعني لان احيانا الواحد ما يكون متخيل هو عن شنو قاعد يتكلم. ما في شيء. I'm not saying that your question is stupid. I'm not saying that at all. يعني لا تفهم كلامي غلط. انا ابيك اول شيء تفهم على اي ليفل مال structure احنا قاعدين نتكلم. This is something which we said at the beginning of this chapter. High level of structure are we talking about? We are looking at
atomic.
the atomic. Yes, at the atomic. So you are looking at the atoms. You
It's
want
hard.
to, huh?
It's hard and expensive. Right.
Exactly. It is not that it's not doable. انت قاعد تتكلم عن تخصص اللي هو nanotechnology, which is a new specialization relatively. يعني this is there الحين for the last maybe 10 to 15 years, and this is being used to manipulate a lot of characteristics of materials, يعني features or properties of the materials. Yes, on that level that we are talking about, on the atomic level احنا قاعدين نتكلم عن 1 times 10 to the minus 9 تقريبا، صح؟
Yes.
And then, so on that level, yeah, it is possible to do that, but it is very costly طبعا. That this is not close back directions. They take an atom there from somewhere and they move it and they put it in the place there. They cause more close. If you cause more close back directions in the material, you are changing kind of you're changing the crystal structure. But this is expensive. يعني all the lattice, كل اللاتس صاير هاللون مثلا. Let's say هاللون. It is doable. It's you can change the position of an atom and take it to somewhere else, but it's very expensive to do it for the whole lattice. يعني كل الماتيريال like that. So it's nature. Allah subhanahu wa ta'ala has created some materials to arrange that. يعني we don't arrange the atoms in this way. They arrange themselves in this way. Allah خلقهم كذي. يعني مثلا the alpha ferrite phase of a steel arranges itself like a BCC crystal structure. The gamma ferrite phase of a steel arranges itself in an FCC crystal structure form, a different crystal structure. احنا ما نسوي كذي، هو يرتب روحه بهاي الطريقة. So if all the material is like that, it will be very difficult to go and change everything there. صح؟
صح.
Any other question, guys? We need to stop now for the other guys to be able to see. I'll say keep to see. So let me stop the recording there. علشان ما تطول. لا مو dismiss. أنا غلط. Stop recording. Stop recording.